Let's look at a famous probability problem called the birthday problem, and sometimes also called a paradox because the result is a bit unintuitive. So, in a group of people, what is the probability that at least two people have the same birthday? So, at first, it may seem like we need a pretty large group before this probability becomes significant, because you might think, well, there are 365 possible birthdays, right? But the answer is going to turn out to be surprisingly small. And so, first of all, we will make some assumptions on the problem. So, we're going to assume that each year has only 365 days. So, we're going to ignore leap years. And second, we're going to assume that birthdays are equally likely and independent, right? So, this is not too bad of an assumption. It's only one extra day. I mean, the second one actually, if you don't have this, you probably it can actually be more likely that you even find people because if their birthdays concentrate around a certain date, then it's even more likely. So this doesn't make the problem behave in some weird way. If it's already likely for this, it's going to be likely for other settings. So yeah, so let's try to compute this. So and how do we do that? Well, we're going to do it same idea that we have done before. So we want to know what's the probability at least two people share a birthday. And that can be quite complicated somehow because you can have, well, maybe the first person and the second, the first and the third, and all those combinations and so on. And the idea here is it might be easier to look at the complement. So if we look at the complement, what's the probability? Oh, so what's the complement of two people sharing a birthday, at least two people sharing a birthday? It's the probability that no one shares a birthday. So let's compute that. Let's compute what is the probability that there are no shared birthdays. And again, here we're saying, let's say a group of n people. So there are no shared birthdays. Well, so what is that probability? So let's count. So if you have n people, how many choices do you have for the birthday of the first person? Well, you have 365 days to choose from. Now, for the second birthday, if you don't want anyone to share birthdays, you have to remove the day from the first person, so you'll have 364. And then again, the third person cannot share birthdays with anyone before, so there are two of them before, so you'll have 363. And you continue to multiply this for all your n people, so minus n minus 1. So here you have n people not sharing, let me put a parenthesis here, n people not sharing the birthday, right? Okay. And what is the total amount of birthdays that you can have? Well, 365 to the power of n, right? Each one has 365 choices for their birthdays. Now, you can multiply on top and bottom by 365 minus n factorial. If you multiply on the top and the bottom, just to simplify the expression a bit. And what you get is that the probability of no shared birthdays is going to be 365 factorial divided by 365 minus n factorial times 365 to the power of n. And so what we are interested in, which is what is the probability that at least one shared birthday. So this probability here, well, it's going to be 1 minus the probability above. So this will be 365. Let me improve this 6 here. 65 factorial divided by 365 minus n factorial, 365 to the power of n. And so this is the exact expression, and one can go and compute it. you do have at least some nice canceling out here with the factorial, but you do have a 365 to the power of n, which might be a bit annoying to compute in certain, if n starts to grow a bit. So let's take a look of how we can actually also like show a different approach to this where we can get an approximate probability. So here, let's say again, let's compute again the probability of no shared birthday. So the probability of no shared birthday, we said another way of writing it is, so if you go over here and you think of this 365 dividing each one of these independently, you can actually rewrite this to be a product here from k equal to 0, n minus 1, of 1 minus k over 365. And the idea is that when k over 360 is small, so at least for small numbers, we can use an approximation. We can approximate. And so this approximation, you can get it from like a Taylor series expansion. So exponential of minus x is approximately 1 minus x, right? So this here, you can approximate it by a negative exponential. And so if we take this expression here, let me copy it. So if we take this expression here, we can actually rewrite it approximately as a product k equal to 0, n minus 1, of exponentials of minus k over 365. And the nice thing about exponentials is that when you take their product, so if you take, let me write it up here. So if you do exponential of x times exponential of y, it's exponential of x plus y. So you get a sum of the powers. And so if we write that, this is just going to be the exponential of the sum of the powers. So what is the powers going to be? It's going to be minus, and then 1 plus 2 plus 3, all the way to n minus 1, divided by 365. So notice that this is going to be 1 over 365, but well, with a minus in front, right? 2 over 365, 3, so it's this sum here. And we've seen before, so let me also write this here. We've proven before that the sum of this, we've done it by induction, was equal to n minus 1 over 2. So remember the sum of the first n terms, we did this proof by induction here, so you can replace it with this here. And so we can rewrite this as exponential of minus n minus 1, and then 365 times 2 is 730. And so we have this expression here, which means that what we're interested in, the probability of at least one shared birthday, is going to be approximately equal to 1 minus exponential of n minus 1 over 730. And with this, this might actually be a little bit easier to compute on the calculator, right? You just, or at least if you have the exponential on your calculator, it might be much easier to compute or in the computer. And one of the ideas here, or one of the things that becomes clear here, is that notice this n times n minus 1 term here. So that means that this is like order quadratic, which means that this exponential goes to 0 very quickly, right? It goes with the exponential of the square of people to 0, which can be quite quickly. And if you compute it out, the surprising result is that with only 23 people, the probability of a shared birthday is already slightly over 50%. And this tends to be quite surprising to many people, that in a room of 23 people, it's more likely than not that 2 of them share a birthday, right? And so, and the surprise many times comes again because many people think, well, 23 is such a small number compared to 365, right? But the point is that you're not actually comparing 23 to 365, because the idea is that we are comparing the pairs of people. So the idea is, if you have a room with 23 people, in how many ways can you choose 2, right? How many pairs do you have? So you have 253 pairs of people, right? And each pair is a chance for a match. So it's not the 23 that you need to think of, it's this 253. And so the birthday problem shows this important lesson, that collusions can happen much sooner than we might expect, because of this quadratic growth of the number of possible pairs.